Right, so if we're going to describe what the direction of the current is, I don't think we can do so by just saying right-hand rule when it comes to Faraday's law. I think you have to give a more reasonable explanation. I think you have two choices here. You could use motional EMF, and I would probably accept that, but let's talk about Faraday's law. Because if you're asked to address Lenz's law specifically, we need to talk about change in flux. So I really want to hit that one today. So the magnetic field is into the board as the bar slides downwards. What's changing? Is it the magnetic field, the angle between the magnetic field and the area, or the area? Which thing is changing? Nope, magnetic field staying the same. The area is changing. The bar is sliding downwards, the area is getting bigger. If the area is getting bigger, the flux is getting bigger. Flux is just a product of magnetic field times area. So we have an increasing flux into the board. What does Lenz's law say has to be the resulting direction of current? So it has to be a current created that will oppose the change in the flux. So the current that's being created has to itself create a magnetic field that is out of the board to be in opposition to the change in flux. So pick any of these wires. Use your right-hand rule at that moment to indicate, all right, it's got to be that way. So the current has to be to the right. In discussing Faraday's law and Lenz's law, you've got to make your argument about the rate of change of the flux. Everybody follow? Now, this one, we probably could have made a very reasonable ILB argument or QVB argument by just picking a charged particle on the bar, saying it's moving downwards and the magnetic field is into the board, and the right-hand rule would have told you right away that the force on the particle is to the right. Just don't want you to get in the habit of that when it comes to Faraday's law if we can avoid it. All right, so I need another table to tell me what they got for the terminal velocity. So, Hoth, did you guys get the terminal velocity?
No.
Hogsmeade, did you get the terminal velocity? Can you tell me what you did to get terminal velocity? Okay, I'm going to stop you right there. For you guys who don't remember this from last semester or last year, terminal velocity occurs when the net force equals 0. So if you didn't know that, you couldn't start the problem. But this is a net force equals 0 problem. And go ahead, you indicated which two forces?
The force of the magnetic field, which is ILB, and then mg from gravity. And then I used that flux equation to find, like separately, I went to find the flux, and then use the flux into the equation with the negative and d.
All right, so that's a whole lot of things. So separately, you went to go find something you could use for I?
Yes.
All right, and you went to flux. What did you do there?
So after I found the flux, which was just I gave like I didn't like provide dimensions names for the stuff I just gave it names.
Okay, what name did you give, say, this?
X.
Okay. So something like that.
And then the equation with the EMF equals negative n the derivative of flux.
Excellent.
And do you want the answer? I got negative, well, this one, BD because dx equals v.
All right, I think we got one more step.
And then current equals Q over R. I found I equals BdV over R. And then plug that back into the force equation.
So just to get the terminal velocity, flux, EMF, Ohm's law, 3 points minimum, a net force equation, 1 point minimum, substitution probably, and solving for V. So they could just ask that one question, and I think it's easily 5 points, right? Easily. You did solve this for V, right? So you get mg r over b squared d squared. Help me understand this, because I think it's kind of weird to me. Do you see that causal relationship that's there? This is the things that will control how fast the bar will fall. And I do find it a little unusual. The velocity of the bar, it increases if the resistance increases. Do you find that unusual? And it decreases if the magnetic field increases. It also decreases if the separation of the bars increases. Does this make any intuitive sense to you? Let's talk about setting up the differential equation, because that's what gets us from having no velocity to having the terminal velocity. So although some of these things are probably going to be useful here, not all of them are. So for those of you who didn't know where to begin in this one, I want to give you a starting point, and then I'm going to let you get an equation started. Will the net force be equal to 0 when dealing with the differential equation? Is it balanced or unbalanced? It should be unbalanced. So this is where we say net force is equal to MA. I would make downwards positive. I think you'll be happier if you do. And take a moment and sketch out the differential equation that could be used to solve for the velocity as a function of time. It's largely doing exactly what we just did.
So I did some of the forces, and I had mg minus the force of the magnetic field, which we found to be b squared v over r equals ma. And then for a, I made it dv over dt.
Everything about this sounds good so far. It's great. Now, solving this for V, and let's look at this for just a minute. Do you see any distinction between this equation and what we would have had for laminar air drag? This is the same equation you get if the force of drag is linear with the velocity, except you have K here instead of this whole thing. The K value has always been more complicated. We've replaced it with K because we just want something simple to work the math. But the K value, or the value for K, has always been a complicated coefficient, usually having to do with things like surface area, weight to mass ratio, stuff like that. And this is your opportunity to internally say, for the time being, when I do my differential equation, I might just write this as a constant, and then I can come back. I would encourage you to do so, because I want to know if you can do the next part. Can you come up with this differential equation? We've done it in this class already when it came to the capacitance function. It is the same as the charging a capacitor equation. So you should be able to do all of the same series of steps. And anybody who was in mechanics last year, you should be able to do this in your sleep. So let's see if you've got this. 5 minutes. It should take you no more. It should take you 2 minutes. But let's see if you can do it in 5. This is one of these kinds of diffie-Qs is very likely to be on the exam. Start here with k equals b squared d squared over r. And drop that back in at the end. You should start this by remembering that the process is splitting the differential. So get the differential by itself. It kind of already is. Just going to leave it there. I'll multiply both sides by dt. So split the differential first. Next, collect terms. Anything that has a t in it needs to be on the side with dt. Anything with a v in it needs to be on the same side as dv. Now establish your integral and set your limits. At time 0, the velocity is 0. At time some future t, the velocity is some value of v. Your bottom limit is always set based on initial conditions. Your upper limit is a placeholder for your function variables. You're trying to get v as a function of t, so the upper limit should be those function variables. Now integrate. The left side is t. I'm not going to spend a lot of time with how to get that. The right side, you may have to do something here in order to get this. You have learned technique. What would probably be the most useful technique for the right side? I think U sub would probably be the most useful technique for the right side. I'll pull the M out first, just to give us a starting point. But yeah, I think we're looking at a U sub situation here. So I'm going to say U equals mg minus kv. That'll be my substitution. Now, the good part about that substitution is that it's pretty simple. The bad part is I need to now replace dv with something. So I need to take the derivative of du with respect to dv. So I can replace du with dv. So du dv equals minus k. So now I'm going to solve for du. What am I doing? I'm going to solve for du, and I'll get minus k dv. So minus k dv. Do you know what to do now? Can you guys do the rest? Or do you keep needing me to help? Because we've done all the heavy lifting now, right? Yeah. Oh, good point. Good point. I'm trying to reach because I can't read my own writing right now. So I'll have to solve for dv. There. Now, I know you guys learned in your calculus class to replace the limits with new limits. Is that what you guys have been taught when you do U sub? Or are you taught to just do your integration and then go back to your old limits? Okay, so it doesn't matter. Does it matter to you which one we do? Because I tend to go back to my old limits after I do the integration. So that's what I'm going to do. Natural log of u. And now I will go back to my old function. And that's going to be natural log of mg minus kv evaluated from 0 to v. All right, so that's all the calculus. Now we're down to just algebra. And I know that this is not a small amount of algebra. And again, the fact that they have this in the exam, you've got to really be moving to make it worth it. I'm going to go ahead and move that K over M over here. Going to combine my natural log, bring them together, raise both sides to the same base. Still not great, but at least I'm pretty close to the answer here. I need to solve for V. Still doing nothing but algebra, but I'll move the MG over here. And I'm unfortunately, or fortunately, I'm not skipping any steps because I know we would probably need to if we want to get this done in a reasonable amount of time. I tend to suggest factoring out the mg here and dividing by k. So you get mg over k equals 1 minus e to the minus k over m t, which would be fine, except we can't leave it like this. We have to do more, don't we? We are responsible for putting it in terms that we are allowed to use. So you have to replace the k back with what we substituted earlier. So mgr over b squared d squared, which we knew we had to have out front, minus b squared d squared over m times r t. Yucky, that's it. You have to have the terminal velocity out front. That has to be there. Did I do my algebra bad? Yeah. Yes, there would. I mean, just look at all that. And we are at 17 minutes. That's me only releasing the pause button to write.